Hey, it's Dr. J. Today we're going to be covering 5.5, zeros of polynomials. Just a quick reminder of the terminology. A zero is the x value in which f of x is equal to 0. It's related to an x-intercept, very closely related, in that it will be the x value only. For example, and this is not a real, I'm not going to do out the entire problem, but for example, if you have a -2, 0 is an x-intercept, then x equals -2 is called a 0. So just a reminder in the terminology, I'm asking in this section for zeros, but essentially I'm also asking for x-intercepts. It's just the y value is 0. That's the y value. And then the x value is whatever it happens to be. Yeah, in this case, it's -2. So we're going to be doing a lot of division today and factoring. And so as we move through the examples, I'll remind you of some of the theorems. We're going to need to use the factor theorem. We will probably also use the remainder theorem. Usually we use these in conjunction with each other. And we might, if necessary, use the intermediate value theorem if it becomes necessary, plus some new theorems. IVT stands for intermediate value. I'll go into that in detail if it becomes necessary. It probably won't show up for the beginning of this lesson. Okay, so let's go ahead and start off with an example. Suppose I wanted to find all of the real zeros of the polynomial f of x equals x to the third plus 3x squared minus 78x minus 80. So let's just kind of go through what we would need to be able to do. Now, if you are really, really good at factoring, and I'll give you a little disclaimer, I guess. Nobody's good enough, right? I mean, I've been doing this for 30 years, maybe even longer, and I'm not even an expert. Factoring is so complicated that you could spend the rest of your life studying it, and you will still not be an expert. So this really is sort of a disclaimer in that if you think you're an expert, if you think you're so good at factoring that you can just do it, then by all means, there are a few problems in which you can just take the original problem and you can just say, I'm an expert, I studied mathematics, I learned all these techniques, and I can just go like this, x minus 5, x plus 4, and x minus 4 or something. By the way, I just made that up. I don't know if it's right or not. I mean, it could be right. I don't know. But it's probably not right. But if you were an expert at factoring and you can just read the problem and go, boom, I can do it. For small polynomials, like quadratics and things like that, you could probably do that, right? You don't have to be an expert, but I won't do very many quadratics. Most of the problems in this lesson are at least cubics, and we're going to go higher. Quartic, 4th degree, quintic is 5th degree, and I think we stop at 6 or 7 in this course. Okay, so that's my disclaimer. If you're an expert at factoring, you don't even need to listen to my lesson. You can just look at the polynomial and go, I already know how to do that, and you're done. Okay, and then what you'll do is you'll set each factor equal to 0 and solve for x. Right? And I'm not going to do it because I don't even think this is right. But if you're good at it, you can take that, you can write it as the complete factorization, and then you can solve for x. Most of us are human beings, and we need a system in order to factor a polynomial. If it gets larger than 3rd degree, 3rd or larger, you're going to need some sort of a system. And so what we're going to do is we are going to use the factor and remainder theorems. They kind of go together. It says theorems. That's my abbreviation for theorems. The factor and remainder theorems together to find the factors when the remainder is equal to 0. So in other words, we're going to hope that we get a remainder of 0. Okay. So what are we going to do? What we're going to do is we're going to divide by what we call candidates. Candidates are potential or possible rational zeros. So we're going to divide by the potential or the possible rational zeros. Now, let's just use a little bit of common sense, okay? We're dividing a polynomial, so let's go ahead and write this out. This will be 1, 3, look for any missing terms, no, negative 78 and negative 80. So that's our f of x, that goes in the dividend. And then we're going to divide by numbers that must be numbers that 80 is divisible by. These are factors of 80. Why 80? Because 80 is the last term. You can ignore the sign. So we don't care that it's negative 80. We just care that it's 80. And you could do that for any positive or negative number. Just ignore the sign, take the absolute value, and essentially just say, well, it must be a factor of 80, which is also a factor of negative 80. So we're only going to divide by factors of 80. I don't know why I started with such a big number, because there's a lot of factors of 80. So factors of 80 are 1, 2, 4, 5, 10, 20, 40, and 80. One way to make sure that you get all the factors of 80 is to pair them up. 1 and 80, 2 and 40, 4 and 20. Oh, I missed one. 5 and 16. And then 8 and 10. So I had to squeeze in a few extras here. 8. See, I missed a couple. And I'm glad I did this because I would have never noticed that I missed a couple. You should always have pairs. 1 and 80, 2 and 40, 4 times 20, 5 times 16, and then 8 times 10. I think that's all. If you can think of another factor of 80, then we'll try it. Okay. Now, plus or minus, because I don't necessarily have to get exactly 80. I could get negative 80. I could have a negative times a positive, or I could have a positive times a negative, or what have you. So I have to consider both the possibilities, which is why we're ignoring the signs. We don't care that it's negative. We're going to consider all of the possibilities, positive or negative. So ignore the plus or minus when you're counting the number of factors. Okay, so these are basically our candidates. I'm not going to divide by any number that's not a factor of 80. Because I know that if it's not a factor of 80, right, we have a theorem that says the remainder will definitely not be 0 if the divisor is not a factor. All right, that's the factor and remainder theorems kind of summarized as once. So we're hoping we get 0. All right. So just pick a number and start with it. I don't care where you start. I usually just start with 1. You can start with any number you like if you have a feeling about it, and then just go for it. 1 times 1 is 1. 3 plus 1 is 4. 1 times 4 is 4. Negative 78 and 4 is negative 74. And 1 times negative 74 is negative 74, and that's negative 154. Yeah, which is not 0. I was hoping to get 0, but it's not 0. Okay. Now, I don't know if I'll need this or not. I don't think I'll need it, but just as a consolation prize, note the remainder theorem, Remtham, says f of 1 is negative 154. So even though I didn't get what I wanted, I did get something out of it. And I don't know if this will be useful. I mean, I don't know. I'm just going to put it aside. It might come back and be useful later. All right, so unfortunately, if you don't get 0, you have to start over again. So you're going to be using a lot of paper here. So you get 1, 3, negative 78, and negative 80. Let's try, you can either move on to another number, like 2, 4, 5, 8, or you can try negative 1, if you like. I tend to alternate. I try a positive, I try a negative, I try a positive, like that. But you certainly can have your own plan. Multiply, add, multiply, add, multiply. Oh, good, I'm glad I did it. Yay! So we know that f of negative 1 is 0. Okay. That's pretty cool, yeah? So that tells me that x plus 1 is a factor of f of x. Yeah, factor theorem and remainder theorem, they work together. They're two sides of the same coin. Okay, and then I don't even have to continue dividing. I know that the other factor is q of x is the other factor. So that would be 1x squared plus 2x minus 80. That would be my other factor. So what have I just done? So now we have x cubed plus 3x squared minus 78x minus 80. That's our f, is equal to d. This is your dx, divisor of x. This is your qx. So that's equal to d of x times q of x with no remainder. So d of x is x plus 1, and q of x is x squared plus 2x minus 80. Okay. So now you have a choice. can either, one, continue factoring, as you learned in chapter 3, or maybe as you learned in another math class. I covered this in chapter 3, but I think what I said was I'm going to give you a very brief demonstration, and I'm going to expect you to kind of pick up the slack with that. Or if the degree of Q is 3 or larger, then keep using synthetic division. I'm going to choose choice 1 because the degree is small. I can easily factor Q of x using old school methods. This would be x plus 10 and x minus 8. Just like we learned in chapter 3. It's a quadratic. You can just factor it using techniques from chapter 3. You want to make sure it's right, yeah? X plus 10, x minus 8. If you add 10 and negative 8, you get positive 2. If you multiply 10 and negative 8, you get negative 80. So now we have f of x, which is the original polynomial. I don't even need to write it anymore. I can just write f is equal to d of x. Don't forget about d, x plus 1, times q. But q has been factored, and I don't care what order it's in, x plus 10, x minus 8. And this is what I meant when I started the lesson. If you already knew this 5 minutes ago, you didn't need to listen to me. You just looked at the polynomial, and you've got a mind that just tells you what things are by looking at them. It's not unheard of. I mean, there's certainly people that can do that. I'm not one of them. I can guess, but I never know whether my guess is right until I actually check it and see if it's right. So I didn't guess this, did I? I did make a guess 10 minutes ago, but it wasn't this. All right. And so now you have the factors. And so the zeros are, set them all equal to 0. And so you're going to get x equals negative 1, x equals negative 10. I know I don't need to show the work on this, and x equals 8. So this is how you'll write your answer. Actually, the x is outside the box like this, and just list them out. Negative 1, comma, negative 10, and then comma 8. And I don't care what order they're in. Don't use any parentheses. And then I don't care what order they're in. If you care, that's fine. Some people really like to put them in order. So I would put negative 10, then negative 1, then 8. If you really want to do that, that's fine. It's not going to matter. It's essentially just a list of answers, and the list can be submitted in any order. Okay, so that's the basic technique. So this gives us a theorem. If f of x is equal to an x to the n plus an minus 1 x to the n minus 1 plus a2 x squared plus a1x plus a0, then all possible rational zeros, some people call them rational roots, are of the form plus or minus p over q, where p is a factor of a0. There's your a0, the last term. So for example, the one we just did, that was 80. Yeah. So I did plus or minus all the factors of 80. And if there's a leading coefficient, then q is a factor of an. So if the leading coefficient is not 1, then you have to list out the factors of that leading coefficient. Otherwise, all zeros, all rational zeros are integers. In other words, integers don't have a denominator. They would just be, as we saw in example 1. So this is sometimes called the PQ theorem, or the possible rational zeros. The symbol for rational is Q. It comes from the word quotient. So sometimes this is called the PQ theorem. Yeah, possible rational. Instead of PR, it's PQ. Okay, let's go ahead and do an example of this. Now, I'm not going to actually solve these ones. I'm just going to list out the possibilities. So example 2. List all possible, also known as candidates, rational zeros of each polynomial. I'm just going to say of each. Obviously, they're polynomials. That's all we're doing in this chapter. So. Oh. It doesn't really matter what the degree is. Doesn't matter if there's any missing terms. All that matters is the first and the last term. Okay, so this is just a list. In the future, I will make the list and then use that list to actually solve the problem. In this example, I'm just demonstrating how to make the list. Okay, I hope I gave myself enough space here. I don't know. Let's see. If not, I might have to move some stuff around. So you have your an. Excuse me, your a0, and then there's your an. This is called a5. Yeah, n is 5. So n is the largest power. It's called an nth degree polynomial. And then we have the leader is A5. So let's do a little scratch work, okay? Factors of A0 are 1 and 7, plus or minus. I'll put that in later. Factors of A5, 1 and 2. So that means my possible rational zeros are plus or minus P over Q. So plus or minus 1 over 1. 1 over 2, 7 over 1, and 7 over 2. I really didn't give myself enough space, did I? So notice how I did that. 1 over 1. 1 over 2. Then I cross off the 1 because it's done. Now I do 7 over 1, 7 over 1, and then 7 over 2. Now you need to make a list. Here's what I'll do. Why don't I just copy this one down here. And then move this one down here. I mean, you're writing on paper, so you can probably just take out another piece of paper, but I can't. And now I've got some more rooms. So the list of possible rational zeros is 1, 1/2, 7, 7/2, -1, -1/2, -7, and -7/2. And I don't care what order you put it in. Those are your possible rational zeros. So all of this up here was just scratch work. If you can do all that scratch work without scratching it out, then that's fine. Okay. All right, part B will be a little bit easier. Part B, we have our A0 is 12. So factors of 12. Factors of 12 are 1, 2, 3, 4, 6, and 12. And your AN, A6 is 1. A6 is 1. So that means all possibilities are just factors of 12. In other words, there are going to be no fractions. So go ahead and list the possibilities. Possible rational zeros. And again, this is just a list. This doesn't mean that they're all correct. It's just saying these are the ones that could possibly be correct. So you have 1, 2, 3, 4, 6, 12, -1, -2, -3, -4, -6, and -12. And again, I don't care what order you put them in. Some people like to go positive, negative, positive, negative, positive, negative, positive. That's one way to do it. Some people do all the negatives first and then all the positives. I can see why someone would do that because it looks neater. Negatives go on the left, positives go on the right. Yeah, I don't care. It's just a list of numbers. I don't care what order they're in. All right, and then we just have to move part C up here. I didn't call this one function. I just called this y, but it is still a function. It's a function with its generic name, y equals. All right, so we got our A0 factors are 1, 2, 5, and 10. All right. Again, you're ignoring the sign when you make the factors. So A3 factors are 1, 2, 3, and 6. Okay. And you can ignore the plus and the minus for now because you're going to put them into your list anyway. Yeah. So we don't care that that's negative. We don't care that that's positive. We're going to make a list of half and half positives, half negatives every time. All right, let's do a scratch list first. So you always want to put the A0s on top and the A3s or ANs on the bottom. Okay, N is 3, so these are your A3s or AN, whatever you want to call it. All right, so make sure you know who's on top, who's on bottom. So have a plan, all right? So I go one number at a time. So 1 over 1. Plus or minus reminds me that I'm going to make 2 lists when I'm done. 1 over 2. 1 over 3, 1 over 6. Now 1 is done. All right, 2. 2 over 1, 2 over 2, 2 over 3, and 2 over 6. Now 2 is done. 5. 5 over 1, 5 over 2, 5 over 3, 5 over 6. Now 5 is done. 10, 10 over 1, 10 over 2, 10 over 3, and 10 over 6. Now, the reason why I call this a scratch list is because if you enter in this, it's not going to be right. Okay, you need to simplify and remove or avoid duplicates. I don't know if avoid is the right word for it. Remove. I like that word better. You can say, well, I avoided it, but it still happened. If it happens, remove it. Get rid of it completely. So here's our list. List of possible rational zeros. I hope I can fit it in this box here. I'll try to write small. All right, 1. 1/2. 1/3. So far, so good. No duplicates. 1/6. 2. All right, you got to simplify it. 2 over 1 is 2. All right. 2 over 2 is 1. That's a duplicate. So remove it. Well, now, I don't mean remove it from the list. Just don't put it in the list. Remove it from your scratch work here. All right. 2/3. That's new. 2/6. 2/6 is the same as 1/3. So that's a duplicate. Got to get rid of that one. 5. 5/2. 5/3. 5/6. All right. So far, so good. 10. Again, don't put 10 over 1. It's 10. Now, 10 over 2. 10 over the 2 is the same as 5 over 1. That's a duplicate. Remove it. 10 thirds. And then 10 sixths is the same as 5 thirds. So 10 sixths needs to be removed as well. Now, there used to be a program that allowed you to just type it once, and then that it counted it for pluses and minuses. That was the program that you had to pay for. In the program that we're using for the homework, you have to type all the positives and the negatives. I don't know if I have enough space here, so I'm just going to try to squeeze them underneath. -1, -1/2, -1/3, -1/6. And hopefully you can see that. -2. If you can't see it, you can just hear me. Take all the positives and then add in all, and then duplicate them, making them all negatives. Although I guess they're not really duplicates if they're negatives. They're opposites. One trick, if you guys are, computer savvy, is you could do the Control Copy, Control C, Control V, and then you just paste the whole list in with a bunch of negatives in it or something. I don't know. You guys can figure that out yourself. Okay. I think that's all of them. Yeah, that's all of them. So positives and negatives in any order that you like. Okay. So let's do one now. Let's do an actual problem now that we have this technique. So for the rest of the lesson, I'm going to do this list on pretty much every problem. I mean, there might be some problems where I can skip this, but for the most part, before you set out on a factoring problem or finding the zeros, you want to at least have something to start with. So that was a long example 2. So here we go, example 3. And there goes my camera. Thanks a lot. What's going on with this camera? Ay, ay, ay. Okay. Come on. Come back to me. All right, let's try one. So find all the zeros and factor completely. The order doesn't really matter. If you're going to factor, then you are going to know what all the zeros are. And if you are going to find all the zeros, then you are also going to know how to factor. But you do need to do both in some of the problems, although some of the problems only ask for one of these two things. But they really are like, heads and tails. I mean, if you have a coin with a head, it obviously has a tail, whether you're looking at it or not. If I could just get my camera to focus, we can begin this problem. Come on. There it goes. Okay. So what do we got? We got P and Q. So let's do our list. So we got plus or minus all the factors of 75. So factors of 75 are 1, 5. What else? 3. What else? 25. If If you have to, actually divide it out, 75 is 3 times 25. 25 is 5 times 5. So 15 then. 3 and 5 is 15. 25 and 3, and then 75. I almost didn't find 15 until I drew the little factor tree. And then you have the factors of 16. 1, 2, 4, 8, and 16. That one's relatively simple, right? 1 times 16, 2 times 8, and then 4 times itself. But again, you don't want a duplicate, so you don't put 4, 4. 4 represents 4 times itself. Okay. Now, again, if you want, you can make this list in your head. If the problem is not specifically asking you to make the list, then feel free to just think of this list. I would probably write it down, though, and then use it as you're going through. So you got 1 over 1, 1 over 2, 1 over 4, 1 over 8, 1 over 16. It's a big list. So 1 is done. 3 over 1, 3 over 2, 3 over 4, 3 over 8, 3 over 16. What else? 5 over 2, 5 over 4, 5 over 8, 5 over 16, 15, 15 over 2, 15 over 4. Oh, man. I guess it's good practice. 15 over 8, I crossed it off a little bit too soon. 15 over 8 and 15 over 16. 25, 25 over 2, 25 over 4. I hope this list shouldn't, it's kind of intimidating, but you're not going to use the entire list. It's giving you, saying, well, your solutions, your zeros must be from this list. At least the rational zeros must be from this list. 25 over 16. I don't think we have any duplicates. 75, 75 over 2, 75 over 4, 75 over 8, and 75 over 16. Okay, so these are the candidates. So now when I do my synthetic division, I recommend starting plus or minus. By the way, if you had to type this list in the computer, look how big the list. I hope this is not one of the questions. You would have to type this entire list twice, once with positives and once with negatives. When you're doing it on paper, you can just put plus or minus, and that applies to the entire list. Let's find the ones that look reasonable. 1, 3, 5, 15, 25, and 75. Basically, the numerator of all of these fractions. I always recommend starting with those. So we're going to take our synthetic division, and we're going to start. I usually just start with 1. 16, 112, 175, and negative 75. If you have a feeling about a number, then try it. You don't have to go with 1 every time. 1 is kind of like, I don't know what to do, just start with 1. You're hoping you get a remainder of 0. That's what you're hoping for. So let's see. 1 times 16, negative 112, and 16 is negative 96, I think. I don't have my calculator handy, but I hope so. All right, 1 times negative 96 is negative 96. And then 175 and negative, I don't think it's going to work. Let's see, 175 and 90. I just might as well just get my calculator so I don't have to stop and think every 2 seconds what's going on here. Yeah, so that's negative 96, and then 175 minus 96. I should have been able to do that in my head. 79, 79, negative 75, 79 is 4. Okay. So that's a no, but I could just, before I move on, I could just note some notes to myself. I might need these later. F of 1 is 4. That might turn out to be useful later. Right? Because think about what that means. That means that it's close to 0. I mean, 4 is pretty close to 0 on the grand scheme of things, right? So you have a point where x is 1 and y is 4. So that might help guide you into place. If you do not get 0, you basically have to start over again. You can either erase and start over, or you can just make a new row. You're probably going to use up an entire, spiral-bound notebook with these, because there's going to be a lot of calculations here. I often alternate, but sometimes I get a feeling. I say, I'm going to try 3. I just got a feeling that 3 might work. I just had a little feeling. I don't know. I actually didn't look. Let's see. 3 times 16 is 48. Have your calculator handy for these. So it's negative 64. 3 times 64 is 192, negative 192. 17, negative 17. And times 3 is 51. And then minus 75 is negative 24. So look what just happened. All right, look what just happened. 1 gave me 4, and 3 gave me negative 24. There's a theorem, I said. If necessary, use the intermediate value theorem. Yeah. So recall the IVT, the intermediate value theorem. If you plug in a number and get out a positive, so we got a positive 4, and then you plug in another number and get out a negative. This was something that was briefly touched upon at early part of chapter 5. I didn't really make a big deal about it at the time. It was like a yes or no question. So now it becomes important what that really meant. If the answer is yes, which it is, it's yes, there is a 0 between them. Between x equals 1 and x equals 3. So look here. In your next candidate, don't just pick wildly. Pick a number that you know is between 1 and 3. All right, let's go hunting. Has to be bigger than 1, but less than 3. So we got 3 halves. Yeah. 5 halves. 5 fourths. 5 12. 15 twelfths. Nope, that's bigger than 3. 15 fourths. That's also bigger than 3. 15 eighths, that's smaller than 3. If you're not sure, divide it out, right? 15 divided by 8, 1.875, so that's smaller than 3. It has to be bigger than 1, but smaller than 3. Let's see, 25 eighths, no, 25 sixteenths. 25 divided by 16, that's 1.56. Let's see, 75 fourths. I know 75 halves is not, 75 fourths is not. How about 75 eighths? 75 divided by 8. Oh, that's way bigger than 3. How about, that's like 9 point something. How about 75 sixteenths? That's also bigger than 3. So by using the intermediate value theorem, I now know that one of these 4 numbers has to work. Yeah, I've only got 4 candidates that are between 1 and 3. So let's go with, I'm just going to take them in order. If you have a feeling, go ahead, but I'm just going to go in order. So 3 halves. Now my dividend is still the same. 16, negative 112, 175, and negative 75. Bring it down. 3 halves times 16. 3 halves times 16. Well, divide by 2 and then times by 3. That gives you 24. So you get negative 88. Again, when you're multiplying by a fraction, divide the denominator first and then multiply the numerator. So 88 divided by 2 is 44, and then 44 times 3, I could have done that in my head, negative 132. And you're going to get 43. 44 times 3, 44 times 3 is 132, yep. So you get an odd number. I already know it's not going to work, because look, an odd number is not divisible by 2. But let's try it anyway. 43 divided by 2 is 21.5, and then times 3 is 64.5. So you're going to get negative 10.5. So check it out. Now I know that f of 1.5, right? Let's go up here to my notes. F of 1.5, because that's what 3 halves is negative 10.5. That's even closer. So I can cross this one out and change this to 1.5. And now I know that I have to find it between 1 and 1.5. So it's not going to be 5 halves. Yeah. I can't remember what 25 sixteenths was. 25 divided by 16. Oh, no, that's bigger than 1.5 too. How about 15 divided by 8? That's also bigger than 1.5. The only one that's between 1 and 1.5 is 5/4. So this one better work. Otherwise, I really need to rethink my lesson here, because it all hinges on this value, 5/4. Let's see. 16, negative 112, 175, negative 75. Bring down the 16. Divide, multiply, you get 20. Negative 92 divided by 4 times 5 is negative 115. Get 60 divided by 4 times 5. Oh, look at that. Yay. And that's what I meant about, if you have a feeling or if you have an intuition, you might have thought to do 5/4. I never would have. I never would have thought to try 5/4. You know what I probably would have done? If I wasn't thinking, I would have done 1, then 3, then 5, then 15, then 25, then 75, and I would have gone, oh, God, I'm not finding it anywhere. I keep looking everywhere. So by using another theorem, an intermediate value theorem, it kind of narrowed down my choices so that I'm not looking at this giant list, right? It's like going on a search for something, but you have a narrowed down search area. Right? You always want to minimize your search area. Otherwise, you'll spend the rest of your life and you'll never find it because you're just sitting there searching and searching and searching through numbers without using any other guidance, right? You need to have a compass, essentially, a mental compass that tells you where it is. All right, we did it. That took a while, but we finally did it. Now we don't need this list anymore. If you're starting with a cubic, if your problem starts with a cubic, you only got to get 1 to work. So we know that x minus 5/4 is a factor. X equals 5/4 is a 0. Zeros and factors are opposite of each other. The other factor, now I was calling it Q earlier. I'm just going to say the other factor and not bother introducing another variable here. 16x squared minus 92x plus 60. And you can factor this using basic math or basic algebra. All right, we call it the old school method, right? There's no fancy new technology. It's just, what do you think it is, okay? Couple things you can do to make life a little bit easier here. You can pull out a 4. What's 92 divided by 4? It's 23. And 16 divided by 4 is 15. Okay, and then now you can factor out, let's see, x minus 15 and x and 4x plus 1. Again, I'm just guessing. I don't know if that's right. Let's check. I hope it's wrong, actually, so you can see how to guess. So I got 4x squared plus x minus 60x. Now, I'm trying to get 23x here. It's 23x. That's a plus sign, and that's an x. So no, I'm not even going to go with that. Let's try another guess. Let's keep guessing. 4x squared. Don't forget you have this 4 on the outside. It's still there. 4x squared minus 23x plus 15. Let's try another guess. You could try something like this. 2x and 2x and 5 and 3. Positive and negative. We try that. Let's see. 2 times 2, I'm just checking here, 4x squared. 2 times 5 is 10x and 6x. That's not going to be 23, so no, that doesn't work. If you get really frustrated with factoring, you can use the quadratic formula. I'm not going to do that on this problem. I'm going to just keep trying until I get it. Let's see. How about 4x and 15, and then x minus, no, it can't be 1. How about x plus 1? No, they both have to be minus. We're trying to get 23 here. 23 is the goal in the middle. Now you get to see what it's, I don't know what the answer is. My guess is as good as your guess. I'm just guessing. So let's see. How about 4x? You guys know this trick? It's called the AC method. If you guess 3 or 4 times and it doesn't work, you multiply A and C. I don't use this trick very often because I normally get it after 2 or 3 guesses, but I know I'm being filmed here and I don't want to waste any more time guessing. So the AC method, you multiply A times C, you get 60. And then you make your little X box here. You want to multiply to be 60, but add to be negative 23. So what numbers multiply? Oh, that's 20 and 3. There you go. There it is. Negative 3 and negative 20, if you multiply them, you get 60. If you add them, you get negative 23. So there it is. So it's x minus 3, x minus 20, and then you got to divide these by 4. So it's x minus 3/4 and x minus 5. And so now my guess is going to be 4x minus 3 and x minus 5. Just take this denominator here, this 4 that's in the bottom right here, and bring it up to the front. So it goes right here. And then don't forget you have another 4 out in front here as well. Now I know this is going to be right, but I should still check it. 4x times x is 4x squared. 4 times negative 5 is negative 20x. God, I just wish I would have guessed this 5 minutes ago. Negative 3 times x is negative 3x. There it is. Look at it. Negative 20, negative 3. There's your negative 23. And then negative 3 times negative 5 is positive 15. Check. I don't need to go any further. I know it's true. Okay, so let's list out our factors now. 4x minus 3 is a factor. So x equals 3/4 is a 0. Right. I hope I don't need to show that. Just take this equation, set it equal to 0, or take this factor, make it an equation by setting it equal to 0 and solve it. All right. And then x minus 5 is a factor. X equals 5 is a 0. I will make a note. 4 is a factor with no 0 because it has no x. So if you have a factor with no x, it's still considered a factor. It's just a factor that doesn't give you a 0. All right, that was a really long example, but it just goes to show that a very simple problem can have a very long, drawn-out solution. Let me write out the solution now. So the zeros are, and just list them out. I don't care what order they're in. 5/4. 3/4 and 5. And then the complete factorization is all of the factors, x minus 5/4, 4x minus 3, and x minus 5. and 4. I don't know what just happened. It got blurry on me. Come on, come back to me. Well, so don't forget the factor that does not give you a 0. So it doesn't show up in your list of zeros, but it does have to show up in your factors. It just does not become a 0. All right. What some folks like to do is to put this factor in and write it like this. 4x minus 20 divided by 4, which just is 5 again. And then you don't have to worry about forgetting it if you keep it inside one of the factors. Whew. Well, now you know what you're in for. Should we try another one? I think we only have time for one more, and then I'll have to continue this with a part 2. Was that only example 3? Are you kidding me? Okay, example 4. So basically the same question. We'll kick it up a little bit. We'll have a 4th degree polynomial, 6x to the 4th minus 19x cubed minus 32x squared plus 52x minus 16. Okay, and you have a choice. You can just jump right in, start factoring it, or start dividing and see what you get. I recommend at least making a loose list of candidates. So mentally, kind of just so that you have some idea of what the candidates are or the possibilities. If something is not a candidate, then don't bother with it, right? So it's going to be plus or minus the factors of 16. That's 1, 2, 4, 8, and 16 divided by the factors of 6, 1, 2, 3, and 6. So this is sort of a loose version of the list. It just sort of gives you something to start with. So you know it's going to be plus or minus 1, 2, 4, 8, 16. What else? 1/2, 1/3, 1/6. And I'm just going to say et cetera, et cetera, et cetera. The list keeps going, but for the most part, you're just going to start with candidates that you feel comfortable with. And I usually start with 1. And you know what? I've had, a feeling that says it's not going to be 1, and then it ends up being 1. And then I've had a feeling that says it's going to definitely be 1, and it ends up not being 1. So I've not been able to narrow down the thought versus the feeling aspect of it. Sometimes a feeling is just a feeling and it doesn't really mean anything. Let's go ahead and see. So bring down the 6. 1 times 6 is 6. Negative 19 and 6 is negative 13. 1 and negative 13, negative 13, negative 32 and negative 13 is negative 45. 1 times negative 45 is negative 45. What's that going to be? 7. 1 times 7 is 7. And then we end up with negative 9. Let's double check that. 1 and 6 is 6. Negative 13. Negative 13. Negative 45. 5. 7. Good. It's negative 9. So no, but I could put this in my mind here. F of 1 is negative 9. That might come in handy later. It might not, but to just disregard it completely would not be wise. So let's try another one. All right. So now you have a choice. Do you keep blasting through the positives? 1, 2, 4, 8, 16. I've had students do that, colleagues and people that I've experienced. Everybody's got a different way of doing it. Say I do all the positives first and then I do all the negatives or whatever. In my next edition, I might have another theorem. In fact, I will have another theorem that'll help you narrow down even further. I don't really have that right now, so I'm just going to alternate. Plus minus until I get one, right? So let's try this one. So that'll be -6, -25. +25, -7, +7, 59, -59, checking my signs, and my remainder is still negative. It's a -75. So again, no. I could write this down. It might come in handy. F of -1 was -75. I don't know at this point. So now your guess is as good as mine. You want to keep trying negatives. You want to go back to the positives. What do you want to do? You got to try another number. The general strategy is whatever the degree is, you have to get two you have to get two less than that to work. So the degree is 4, subtract 2, so that gives you 2. 4 minus 2 is 2. That means you have to get at least 2 of these candidates to work. All right. If the degree is 3, like it was in the previous example, then you only got to get 1 candidate to work. All right. I got a feeling about negatives, so let's try -2. I was going to go +2. Let's stick with -2. -19, -32, 52, and -16. There's my remainder. All right, so -2 times 6 is -12. That'll be -31. That'll be 62. That'll be 30. -60. Something's wrong. Oh, no, it's -8, yeah. I was about to panic, yeah. 52 -60 is -8. -8 and -2 is 16. And there we go. We got a 0 remainder. Whew. I was about to panic. So I don't even need these guys anymore. All right. Well, I don't need those failed. I got a good one. I was only going to use those if I just couldn't find another one to work. I don't know if there might have been a mistake in there somewhere, but this is definitely correct. We got a 0. Okay. And we have a factor, right? So we might as well start chalking this up. We have x equals -2 is a 0. X plus 2 is a factor. Let's save our work here. All right. Now here's the thing I've been hoping will happen this entire lesson is when do you get to keep going? All right. Whenever you get a 0 as a remainder, you don't have to start over again. You could just add another row. Bring your remainder box down underneath the new last constant and start over again. All right. So pick another candidate. We tried 1, we tried -1, we tried -2. We could try 4, or we could try -4, or we could try +2. There's lots of other candidates. Go with 4. I'm going to go with 4. So bring down the 6. 4 times 6 is 24. -31 and 24 is -7. 4 and -7 is -28. 2. 4 times 2 is 8. And there it is again. I had a feeling. So now I have x equals 4 is a 0. and x minus 4 is a factor. So every time you get a 0 remainder, you get not only a 0 of the function, but you also get a factor. Yeah. Once the quotient is 3 terms, that's a quadratic. It factors easily. Well, easily is a relative term. It factors easier than the original problem. So I've got 6x squared minus 7x plus 2. I'm going to factor it the old-fashioned way. 3x, 2x, 1, and 2. Now, again, I'm just guessing. These are much smaller numbers than before, so I think it'll be right. 3x and 2x is 6x squared. 2 and 1 is 2. Make them both negative, so when you multiply two negatives, you get a positive 2. And now the hard part, you got to make sure the middle comes out to be 7, or negative 7. But it does, look. Negative 2 times 2, that's negative 4. And then 3 times negative 1, that's negative 3. And negative 4, negative 3 make negative 7. So now you have 3x minus 2 is a factor. So x equals 2/3 is a 0. Again, I'm not showing the math on that. I don't want to insult anybody. If you take 3x minus 2 and you set it equal to 0, that's why it's called a 0, and solve it, you're going to get 2/3. And then 2x minus 1 is a factor. And then so x is equal to 1/2 is a 0. Again, take the factor, set it equal to 0, and solve it, and you'll get 1/2. All right. So we're done. Just got to put all this together. How should we do this? So let's go ahead and list the zeros. Negative 2, 4, 2/3, and 1/2. And then list the factors. I don't care what order they're in. I'm just going to do them in the order I found them. X plus 2, then x minus 4, then 3x minus 2, and 2x minus 1. And then the nice thing about having the coefficients inside is that means I don't have one on the outside. There is an alternative answer for this. If you remove the 3 and the 2, you factor them out, then you would have a 6 in the front, and then these would be fractional answers. They would look like fractions. So I would also accept this 6 out in front, and then you got to write these as fractions. Hardly anybody ever takes this option, but these are the two different ways of writing the answers. Okay, so you got your zeros and you got your factored completely. So in my next episode, I am going to give you another theorem that's going to narrow down the trial and error a little bit so we don't have to try as many possibilities. We'll do a few more cubic examples, and then I'll kick it up to the more complex problems, either with higher degree or maybe with irrational numbers or imaginary numbers or something like that in the next edition. But until then, this is Dr. Jordan. I'll see you on the internet.